I'd like to introduce the next speaker, Julienne Stroeve. Julienne's also from University of Colorado, not exactly a cohort. She's, of course, much younger and yet much more accomplished than I. She's an expert in both remote sensing and climate and sea ice in the Arctic, and she will talk about that right now.
Thank you, Martin, and thank you, Mark Serez, for that great talk and helping to set the stage for my talk. Before I begin, I would like to acknowledge all the folks who have helped contribute to this talk, especially Marika Holland. Let me get to my slide. I forgot I don't have my intro. Marika Holland at NCAR, who's been very valuable at helping me work with the climate model data and interpret results from those climate models. I'd also like to thank Ron Kwok and Jay Twally for sharing with us their ice thickness fields derived from ISAT. And also we have several people at the University of Colorado and NSIDC that have been contributing as well, such as Sheldon Drobot, Jim Maslonic, Andy Mahoney, Walt Meyer, and Mark Serez. So, you know, when I started out about a decade after Mark Serez did in terms of becoming a graduate student. But even in the early 1990s, when I was a graduate student, I never thought that during my lifetime I might actually get a chance to witness an Arctic without any sea ice during the summer times. I mean, sure, I knew about the importance of greenhouse gases and their effects on the climate system, and I understood the importance of the positive snow and ice albedo feedback mechanism, which is certainly one of the reasons I went into studying the polar regions in the first place. But you know, we always had quite a bit of ice, even in the 1990s. And if you look at this animation of September sea ice cover based on the satellite record, you can see that, you know, even in the 90s we had quite a bit of sea ice. And even if you had a low sea ice year, you tended to be followed again by another high sea ice year. There was a lot of natural variability in the system. But things have really changed in the last decade. And now the Arctic sea ice has really emerged as the poster child for climate change. And this is something that's quite different from when I started out as a graduate student. If we look a little closer at what happened in 2007, and Mark Serez showed this slide as well, besides the fact that we have about 50% less sea ice in 2007 than we normally had, if you look at like the 1950s to the 1970s, you know, typically when you had a low sea ice year, it would be confined sort of to the margins of the Arctic basin. So it would happen in the Laptev Sea, or the East Siberian Sea, or the Chukchi, or the Beaufort Sea. And you know, that's how it sort of was in the 1990s. And then in the 2000s, you started having more widespread ice losses, so they were encompassing more of those peripheral seas. And even in 2005, you lost a lot of the ice, throughout most of those regions. But in 2007, all of a sudden now you're penetrating much closer to the Central Arctic. You're moving much further north, and you're starting to encroach on the North Pole. And so the idea that you might now have open water at the North Pole in the not too distant future actually is starting to become a reality. And there's been lots of papers written, a lot of papers that are going to be coming out soon talking about what happened in 2007. And certainly a big factor was that we had this really favorable atmospheric circulation pattern that set up that favored a lot of ice loss, both through surface melting, basal melting, strong winds that helped push the ice away from the coasts of Siberia towards the North Pole. All these things contributed to this dramatic ice loss. But if you had had that atmospheric circulation pattern set up, say, in the 1970s, you may have seen a dip in the ice extent, but it wouldn't have been very noteworthy. And so what's changing? I mean, what is making it now so sensitive? A key thing behind this appears to be the fact that while we've been seeing a decrease in the sea ice extent during the summertime, we've also been seeing this transition towards a much younger Arctic sea ice. And this is results here from an ice tracking algorithm developed by Chuck Fowler and Jim Maslonic, where they use ice motion fields to track individual ice parcels. And so basically, if you have that winter-formed first-year ice and it floats around the Arctic and it survives, at the end of summer it gets stepped up to ice class of age 2, and so on and so on. And what you'll notice that in spring of 1986, more than 60% of the Central Arctic Basin was consisting of perennial ice, and only about 30% perhaps was first-year ice. But this has changed, and you go now to spring of 2007, and now you have more than 50% of that Central Arctic Basin is now first-year ice, and you have only 10% of that ice that is now 5 years or older, which is shown in red, whereas in the past, in 1986, it occupied a much larger portion of the Central Arctic. And in fact, now it's just found sort of in this narrow region north of Greenland and the Canadian archipelago. So a big change. And certainly one of the reasons we've seen this transition is partly a result of the positive AO period that happened in the early 1990s, which helped to advect a lot of that ice, that older ice, out of the Arctic Basin through Fram Strait. And so we did see a lot of this happening. Part of the shift can also be due to just warming atmospheric and oceanic temperatures also playing a role. But the end result is we have a much younger ice pack. And this is important because that younger ice is thinner ice. And this is some results from a study that was published in December by Jim Aslonick, where we made a comparison between 4 years of ice age data during spring and 4 years of ICESat-derived ice thickness fields. And you can see that, for ice ages of 2 years and older, you get a nice linear relationship between the age of the ice and the thickness of the ice at a rate of about 0.2 meters per year, until the ice gets to be about 3.2 meters thick, and then that relationship starts to fall apart. But if we were to then take that information and use this linear relationship sort of as a proxy to go back in time and look at maybe what the changes in ice thickness have been based on age, we could infer that there's been a decrease in mean thickness of about 2.6 meters in March of 1987 to about 2 meters in March of 2007. So basically you're ending up now with a very thin Arctic ice pack that then becomes much more vulnerable to natural variability. So events like what happened in summer 2007 can now cause large areas of the Arctic ice to melt out in the summertime. So what about conditions for now? Well, it took a little while for the Arctic to refreeze this winter, and for example, freeze up in the Chukchi didn't happen until about mid-December. But once it cooled enough and the ocean lost its heat, the freeze-up began pretty well, and we actually saw some partial recovery compared to conditions last year. So here I'm showing the sea ice extent from the beginning of February of 2008 through sort of the beginning of May here. And you'll notice that the blue line is for 2008, and the dotted green line is for 2007. And yeah, there was some recovery, at least compared to the previous winter. But compared to the long-term mean, which is shown by this gray line, we're still quite a bit below normal. And now we're looking at sort of end of April, beginning of May, and we're starting to come close to that number in 2007 already. But just looking at ice extent doesn't even tell you the full story, because if you look at the ice concentration anomalies, and now this is for the month of April, you'll notice that in the eastern Arctic, we have much lower than normal sea ice concentration, and in the western Arctic, we have higher than normal. And this is a pattern in the sea ice fields that we typically see when you have a positive Arctic oscillation winter. And so this winter we saw a return to the positive phase of the Arctic oscillation, which helps to advect warm air into the eastern Arctic, which then also, besides reducing the sea ice concentration, you also get a lot of new ice formation in this region. And so we just have an anomalous coverage of thin ice in the eastern Arctic. Now, what about ice age? Well, if we look at conditions right now compared to 2007, there's been a huge shift in the age of the ice in the Arctic during March. So here we have 2007, and here we have 2008. Again, the red here is age at 6 years or older, the dark blue is first-year ice. And you look at that and you see, well, here in 2008, 73% of the Arctic basin is now first-year ice, compared to about 58% in 2007. Now, of course, you would expect there to be a lot more first-year ice in 2008, partially because we lost so much ice in 2007, so you had a lot more open water areas in which new ice could form. Part of it also is the fact that you did have the return of the positive mode of the Arctic oscillation, which helps to advect some of that older ice out of Fram Strait. So some of that ice loss could also be a result, or the loss of the older ice is also a result of atmospheric circulation patterns that set up this winter. But when you look at this and you think, wow, we're starting out this summer melt season with a very vulnerable ice pack. And if we look at that and we look at ICESat freeboard estimates, and this is some data we recently got from Ron Kwok. Again, we're looking at spring of 2007 compared to this spring in 2008. And you will notice that the freeboard suggests, we have a much thinner Arctic ice pack this year than we had last year. We get about 5 to 10 centimeters thinner in the seasonal ice cover, so all of this blue area. But even if you look at the older ice, you see quite a big change in the ice thickness fields. Now, I do need to caution that this is freeboard measurements, and so this includes the snow cover above the sea ice, because we haven't removed the snow cover yet. And so you could, if you had a thin ice cover with a thick snow, or if you had thick ice with thin snow, they may look exactly the same. And so we really need to correct for the snow cover in order to get a really true idea of what the ice thickness is. And there is some evidence from some folks I've talked to recently that it looked like there was a little bit less snow this year in the Arctic than there was the year before. And part of that certainly could be the result of the fact that it took so much longer for everything to freeze up, so you didn't accumulate all that snow yet. But even so, it looks like, we're very, very thin right now. If we wanted to use the relationship between age and thickness as a proxy for ice volume, we can make a figure such as this one, where we can look at changes in ice volume. So starting here in 1985 and running through 2008. And if we do that, you get this big decrease that's happening through the 1990s, and then you get some partial recovery after the AO became more neutral, and then it started to go down again. And our least amount of ice volume right now is in 2008. And this is based on this linear relationship that we had from 4 years of IceSat data and ice age data. But this value might actually be even less if those relationships no longer hold. So if that older ice is actually thinner now than it was 2 years ago, we could actually see even less volume in the Arctic right now of ice. I also want to mention that right now things are very warm. So the melt season has begun in the Arctic, and this is April 2008 air temperature anomalies relative to 1979 through 2007. And even though the spring is a little bit colder than it was last spring, it is still very, very warm. We have very warm temperatures over Novaya Zemlya, which actually is a result of the fact that there's a lot of open water in that area, so you have a lot more heat transfer between the ocean and the atmosphere. But we also have a lot of warm temperatures here of the Central Arctic and also off the coast of Alaska. So we know the melt season has begun, and that's why we're starting to see this dip now in the ice extent. We're starting to approach the 2007 values. So it doesn't look good just coming into the melt season right now in terms of the summer ice cover. Now, another thing we've been looking at lately is the survivability of that first-year ice. So right now you have 73% of the Arctic basin is covered by first-year ice. Well, this is a time series of the winter first-year ice, which is shown in red, and the amount of first-year ice at the end of the melt season. And you can see there's quite a bit of variability. In 1996, for example, we retained quite a bit of that winter-formed first-year ice. But in general, we tend to only retain about 30% of that first-year ice. And the least amount we ever retained was in 2007. But you look at this high fraction of first-year ice this year, and if you think, well, say we only retain 30% of that, there's going to be very little ice left in the Arctic this summer. And in fact, if we were to go ahead and take survivability rates of all the different ice classes and apply them to this winter's ice cover, we could make a figure like this, where we're predicting the end of summer minimum sea ice extent here on the y-axis as a function of the different years of survivability rates. And this line right here is a record minimum extent that happened in 2007 of 4.13 million square kilometers. And the red line is taking the average of all of these estimates based on these different years. And what you'll notice is only 1 year out of all of those years, if we look at it, where we would not break the record this year. So it's sort of a 1 in 25 chance that we'll probably surpass the record in 2007 if you just base this purely on how likely the ice is to survive this summer based on what it's done in the past. That we won't break the record, sorry. Thank you, Mark. But of course, this is a very simplistic calculation because one of the things that we realize, of course, is, now we have first-year ice so much further north than we've ever had before. So it's encroaching on the North Pole. Whether or not that will melt out this year or not, we don't really know because we've never had so much first-year ice that far north. And, presumably, you get less solar input. You might actually help keep some of that ice. So this is probably, this is a very simplistic estimate. And if you look at some more sort of empirical statistical forecasts of what we might think will happen, people like Sheldon Drobot or Ron Lindsay, they're sort of giving like a 50-50 chance that we might break last year's record. But even so, I think no matter what, even if we don't break this record, I think we're going to be very, very low this summer, just based on the fact that we have so much first-year ice in the Arctic, and this is much thinner than the older ice, so it's much more vulnerable to melting out. So, after the dramatic ice loss in 2007, there's been a lot of discussion if that represented a tipping point. And here I define a tipping point at which the sea ice cover rapidly switches to a new stable, and in this case, a seasonally ice-free state. We often define abrupt climate change in terms of this sort of tipping point type behavior, and that was what was defined in the National Research Council. And we do see that some of our climate models suggest that this transition towards a seasonally ice-free state could actually happen as a result of tipping points, but we also see model simulations that suggest that abrupt change can happen, but it may not actually imply that a threshold's been reached or that you have sort of this unstable equilibrium that then happens. So if I take a closer look, for example, at climate model output for CCSM3. Now we do know from work that Marika Holland has done is that, as you continue to reduce your summer sea ice cover and you continue to thin it, it becomes very vulnerable to natural variability so that you can get these very big abrupt transitions in the ice cover. So here in blue, I'm showing the September sea ice extent from one of the CCSM3 runs from 1900 through 2100. And in red, I'm showing the observations. And in this model simulation, you get this abrupt change around 2024, where all of a sudden you get this huge loss of ice in a single year. And in the case of CCSM3, it's about a 1.8 million square kilometer loss in a single year. And then what happens is, you lose this ice, and then all that open water area helps foster that positive albedo feedback mechanism, and then you get rapid decay of the remaining ice cover. Well, you look at what happened here in 2007, and we lost 1.6 million square kilometers between 2006 and 2007. So it's on the same order of magnitude as what we're seeing in these climate models right before these abrupt transitions happen. It's just happening about 20 years early. And so you look at that and you think, well, are we in that phase now, this abrupt, rapid change in the Arctic? And in some ways, the setup looks right. If we were to compare ice thickness fields in CCSM3 during winter, so during March, prior to one of these abrupt events, so this in this case is for year 2024, and we compare that with the ice set-derived thickness from last spring. And if you look at that, you notice that we are about as thin, or in some areas even thinner, than the climate model shows before this abrupt transition takes place. So here I have a mean thickness in CCSM3 of about 1.71 meters, and the mean thickness from the ICET data is about 1.75 meters. But even though we know that having a very thin ice pack is important for these abrupt transitions to happen, we also know that natural variability remains very, very important in the climate system. And here's an example of mean ice thickness during spring from several runs of CCSM3 as a function of the standard deviation in the September sea ice extent. And what you'll notice is for the thicker ice, you don't get a whole lot of variability. The variability is much reduced for the sea ice extent during September. But as you thin that ice cover and you get to around 1 meter thick mean sea ice thickness, all of a sudden you get a lot more natural variability in your September sea ice extent. And this makes physical sense because you have a very thin ice cover and you get this very favorable atmospheric circulation pattern, such as what happened in 2007, and you can melt out large areas of that ice pack. On the other hand, if you end up with a very cold summer and a cold winter, and you form a lot of winter ice and the ice doesn't melt out that following summer, you'll get a corresponding jump back up in your ice extent at the end of summer. But eventually, as you continue to thin your ice, that standard deviation goes down until all the ice is basically gone. But so, if we look at what happened in 2007, so again, I'm showing the observations in red and another climate model run from CCSM3 in blue. In this case, we didn't have quite as big of an abrupt change in CCSM3 compared to the observations, but there was some partial recovery for a few years. And it went up and down for a while until eventually then you end up losing all of your ice. And so we can't really say with any certainty that, okay, well, since we had this huge drop in 2007, we're now going to lose all of our remaining sea ice because there is a lot of natural variability. And it just so happens if the natural variability works in the opposite direction of that forced anthropogenic change, you might get some partial recovery for a year or maybe even longer. But eventually, that natural variability is going to once again reinforce that anthropogenic change, and you are going to lose all your sea ice cover. So I think it's just an important point to make. And it was interesting, in 1996, we saw something like that happen. We had a very low year in 95, and then there was nothing unusual about the winter ice pack in 1996. You just ended up with this atmospheric circulation pattern that helped maintain that newly formed ice in the Arctic, and you had a big jump back up actually a larger increase between 95 and 96 than we just saw the drop in this last year. So one of the questions is, does thin ice imply a tipping point? Because the idea is if these simulated abrupt transitions are the manifestation of a tipping point type behavior, then you might think that they would be preceded by a similar critical state. And so we looked at this with runs from CCSM3. And so here's an example from 5 years of ice thickness fields before you have these abrupt events. And you can see the solid line that actually represents the September sea ice extent before the abrupt event, and the dotted line is that after the abrupt event. And what you'll notice is that there doesn't seem to be any critical ice thickness or any spatial pattern of thinning that that occurs right before you get these abrupt transitions. So we can't see any sort of critical thickness state that it happens. And don't have time to show this also for ice concentration or for the fraction of first year versus older ice. But the same thing happens in those fields. There's no critical sort of parameter that we can see, at least in the sea ice fields, that precedes these abrupt transitions. But although we don't find that, we do know that in order for these abrupt ice losses to happen, you need to have adequately thinned that ice cover. And that is for sure in CCSM3. And we also see it in other of the general climate models. Here's an example from several climate models. And here you have, again, thickness. And here's September sea ice extent. And so what you'll notice is when you have much thicker ice, you can get large changes in the thickness and volume without a very large change in the ice extent in September. But as you thin that ice down and you get large changes in ice volume, you get very corresponding changes in the ice extent, and you can have very large areas melt out. So in conclusion, we know that our current climate models are underestimating the observed rate of ice loss. Mark Suresh showed a nice slide of that. And the large ice losses that we saw in 2007 typically don't happen until about mid-century in our climate models. If we look at the CCSM3 climate model simulations, we know that there are 3 factors that contribute to these abrupt transitions in the ice cover. One of them is the thinning ice. The other one is pulse-like increases in oceanic heat transport to the Arctic. And finally, then the positive surface albedo feedback kicks in. And what happened in 2007 is very similar in character to these abrupt ice loss events simulated in CCSM3. We had maybe a different atmospheric circulation pattern that kind of caused this rapid meltout, but it was sort of the same sort of mechanisms that we're seeing in CCSM3 is what happened in 2007. Again, the outstanding question that Mark even raised as well remains whether or not these abrupt events occur to a threshold or a tipping point. When we look at CCSM3, it just seems that the ice loss that we see is sort of the interaction between this large intrinsic variability in the Arctic with increasing force change from greenhouse gases. But just because we didn't find evidence of this tipping point in the model data doesn't necessarily mean it doesn't exist. It could also exist in other variables that we haven't looked at. But regardless, the result of this abruptly changing ice cover is going to be the same, whether it's due to a tipping point or whether it's due to the interaction between natural variability and the force changes. And it's going to have considerable impacts on the socioeconomics, climate, and biological systems of the Arctic. Right now, summer 2008 is poised for yet another dramatic retreat of the ice cover. Whether or not it's going to break the record in 2007 is going to depend in large part on the atmospheric circulation pattern that sets up this summer. But I think even if we were to have maybe what we'd call maybe a more normal summer, I think we'd still see very large ice losses. Thank you.